do. Lemon 1 is on sequences. We should just define a sequence. Some of you probably are familiar with sequences, maybe in a pre-calculus course or just a college algebra course. A sequence, what is it? First of all, it is a function. I want to point that out. All right. It's a function. But the domain is interesting. Whose domain is the set of positive integers. So before we get going with doing all these sequence problems, I'll be writing them on the board. We'll be doing some limits and stuff. I need everyone to understand what a sequence is. You're like, well, it is a function, but its domain, those are the x values, right? They're the set of positive integers. So I can even put the set of positive integers right here. That's 1, 2, 3. You notice I'm not putting 1.5 or 2.3. That's what I mean by integers. And 4, dot, dot, dot. Just forever.
So 0 won't be part of the sequence?
That's right. But you're going to find yourself using 0 when we get into 11.2. When we do these series, sometimes we'll start a series, and I'll talk about what that is at 0. But for the definition of sequence, like it's a set of, it's the function whose set of, whose domain is a set of positive integers. So it really means, if I made a table with x and y, all these numbers here every time are going to be what?
Positive.
1, 2, 3, 4. I mean, every time. That's what we're saying. I need everyone to understand about a sequence. The graph would look like a bunch of dots. The graph would look like a bunch of individual dots every time. Because you're not able to put 1.5 and 2.3 into it. You know? But it still passes the function test. Because you draw those vertical lines, you only hit those dots. Does that make sense? Like the graphs would look something like this. And it might be like dot, 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 dot. But what we're going to look at in this section, this isn't a pre-calculus course, this is Calc 2. We're going to look at, well, what's the limit of the sequence as you go towards infinity? And they always use the letter n for x, so I'm going to start that one. You know, here we're just going to be like, let's call this n. This is your domain. And we use 1, 2, 3, 4, every time. So they came up with a notation for the y values of the function. They call it a sub n. I mean, surely you could call it like k sub n or something, but many times they'll call the sequence a sub n, or that's the terms. So I'm going to put that. You're going to hear the word terms. The y values are now the terms of the sequence. The terms of the sequence. But the graph would look like a bunch of dots. Where this is n now, that's right. This is a sub n, y values. But never lose. Try not to lose focus. You're like, this is just a function. Just a bunch of dots. But what we'll be looking at today is this sequence going to converge to a number? Maybe to like a 0. Or does it diverge towards infinity? Or does it diverge towards negative infinity? So when I bring up that word divergent or diverges, we're talking about, oh, it's going towards infinity or negative infinity. To converge to an actual finite value. We'll explore that as well. Hey, so to start, we got to just look at some basic sequences, right? So this may look, the first two examples may look like something from your pre-calc class, but that's all right. We need to start slow. Here's my first sequence. How about nothing crazy? Evan, could you just find the first 3 terms of that sequence? How about that? There's a sequence. Look at the notation. A sub n equals n squared plus 1. That's a sequence. But you're thinking, oh, this is kind of like y equals x squared plus 1, right? Exactly. But by this notation, we're saying it's a sequence. We can't plug in a 1.5, right? We can only plug in what number? 1 and 2. All right, let's find the first 3 terms of this sequence. Oh, I guess it's 1, 2, and 3. You're like, eh. Those are the numbers we'll plug in. The terms will be the y values. Okay. What are the first 3 terms? Plug a 1 in there. What do you get? 2. And you can actually write a sub 1 equals 2. That's the first term. The first, here I'll put it in words. The first term is 2. A sub 1 equals 2. The first term is 2. And you bet, at x equal 1, y is what? 2. If we say is x and y, when we use n and a sub n. What's the second term? Yeah, 3 squared plus 1. What's the, oops, sorry. What's the third term?
That should be 5, Professor.
Yeah, that should be
Oh,
5.
5, thank you. What's the third term?
10.
10. I skipped over one, thank you so much. Oh, the second term is 5. The third term is 10. You can even look at them in if we started graphing this. No, we don't graph in this section, but sometimes thinking about the graph really helps you understand the limits. Would the graph be connected? No, it would just look like a bunch of look. There's 1, there's 2, there's 3. It went from what? 2 jumped up to 5, jumped up to 10, except a bunch of dots. It's not linear, but you can tell it's quadratic, right? So that's just to get started. Those are the terms of the sequence. You hear that word. All right, here's my next example. Got to do one of these. What if I put a parentheses here? And I wrote -1 to the nth power. Info. Let me make sure that stands out. I got too close to that equal sign. -1 to the nth times n squared. That's a sequence. Yeah, but it's very interesting what the -1 to the nth does to it. I like that word. You know what they use in the textbook or most textbooks? It starts with an N. You notice they change, right? What's the first number? Is it positive or -2? -2, good. What happens when you plug in a 2 there? -1 squared is what? Positive, and then it's what? So I want to see what's going on. The same numbers as before, but what's going on with the signs? On those consecutive terms, what's happening every time on a successive term? The sign is what? Changing, so alternating. That's the word. So I like the word oscillating, but they call this is called an alternating sequence. An alternating sequence. So it actually has a word. We're in 11.1, we'll get to 11.2 today. Section 11.5, it's titled Alternating, Series, Alternating Series. Oh, it's going to have -1 to the nth, right? So can we put down our notes, what makes sequences alternate? A -1 to the nth, does anything else do it? A -1 to the nth will do it? Or how about a -1 to the nth plus 1, wouldn't that do it? Anything else? How about a -1 to the nth minus 1? These are just examples of what will make a sequence alternate. So when you see these, you're like, oh, I know that thing's going to be changing from positive to negatives to positives, Kate.
Alternating sequence, doesn't mean both the components of being negative and having an exponent? Or
That's right. It's got to have that -1 in there, and then it has to have the exponent. Because you understand, what if that n wasn't there? Oh, then they're all going to be what? Negative. And I got to be careful. Do you notice I didn't do this? I didn't do that. Because what would have happened? Plug in a 1, what do you get? -1 squared is positive. You plug in a 2, what do you get? It's positive. So I want to point out that will make these 3 will make them alternate. So you're like, should I just be ready for that? You'll probably see them, and you just plug in those numbers, you'll notice they'll alternate. I want to give you a heads up on that. That's what makes sequences alternate. Okay. So that really comes into play when in section 11.5. You can see a bunch of problems that have these in them when we're dealing with the series, which we'll get to later. Series have something to do with sequences. You go, what is it? Well, I might as well tell you right now. You see these terms? In a series, you start adding them up. You just start adding them up. Just sum them. So I guess the series is the sum of the terms of a sequence, right? That's what we're getting. But before we get to series, we've got to concentrate on sequences. So we're just going to concentrate on these sequences. All right. and this is what we're going to explore. What's going on as n approaches infinity? That's what we're going to explore right now, everyone. Can we get this down? This isn't a pre-calc class. This is calculus 2. We know about limits. We want to see what's going on as n approaches infinity. So the wording they use, I want to use the exact wording from your author. He says, determine whether the sequence converges or diverges. If it converges, find the limit. I'll write that on the board. I'm going to repeat that too, because could you let me know, have we heard something like that before in one of our sections previously? Listen to this. Determine whether the, okay, they say sequence, fill it in with another word. Determine whether the sequence converges or diverges. If it converges, find the limit. Do you remember what section they had something like that in?
Improper integral?
Yeah, the improper integrals, Armando, very good memory. That was good. So it's the same directions, but I'll write it out. Okay, determine. And then we'll just do a bunch of problems. Determine whether the sequence converges. Converges. Or diverges. That word diverges, when they're talking about, oh, it goes towards infinity or negative infinity. It just does not exist. It could be any of those. Sequence is heading towards infinity, or heading towards negative infinity, or it just does not exist. What do you mean it doesn't exist? It just keeps bebopping all over the place. It's not convergent to one value. Those dots, you can always think of those dots. Hey, they did write this. If it converges, we will have to find the limit. All right. Find the limit. But please make a note. These aren't series yet, are they? This is the only section on sequences. Then 11.2 to 11.6 will all be series, where we sum, we add up terms. We're just looking at these dots. All right. So here's my first example. How about 3 over n plus 2? How about 3n squared plus 1 n minus 1? Actually, you know what I'll do? Put plus 2. N squared over n plus 1. Let's start with these 3 examples. I'm going to start grabbing some from the book here. They go fast. If you're thinking of these as functions, y and x, y and x, y and x, we're going to do these 3. Do these look familiar? They're rational functions. I know they're sequences, but if you think of that as y and this is an x, if a y equals 3 over x plus 2, and y equals 3x squared plus 1 over x plus 2, and y equals x squared over x plus 1, these are what we call rational functions. They have funny asymptotes, if you recall. So can we just, that's why I chose the 3. Can we just review the asymptotes, specifically the horizontal asymptote? And what we're doing with each one of these sequences, everyone, you're like, how do we attack it? We're going to find the limit as n approaches infinity on each one of these. So I wrote that, but every one of these sequences, on these questions, we're going to look at what's the limit as n approaches pos infinity of the sequence. That's what we're exploring. That's really the directions. And we say if we get an answer like 5, then it converges to 5. The sequence converges to 5. But if you get infinity, we just say what? Diverges. All right, we'll start out with this one. Anybody know about this one? You can look at it numerically or graphically. But does everyone know this thing as a function? Y and x has a horas. You know what I mean by a horas? Has a horizontal asymptote. And you can recognize that because this is a rational expression. What I mean is you got polynomials on top and polynomials on the bottom. And with these rational functions, if the higher power's on the bottom, it always has a horizontal asymptote at y equals 0, the x-axis. So what would this graph do? It would just keep approaching this horizontal asymptote as you keep increasing that. What would it do? Like plug in a 1. What's 3 over 1 plus 2? 1. Okay, so at 1 it's 1, but it'll just keep getting closer and closer and closer to this horizontal asymptote. So what's it heading towards? Think of its a sub n die, the terms. Where the terms heading for? If you're thinking x and y, think of what's the y values heading towards? 0. So this sequence converges to 0. That's what we'll write. You can write our answer like this. The limit as n approaches infinity of a sub n equals 0. Now I looked at this graphically. Could you look at this numerically? It's not a bad idea. I mean, you can look at this numerically. Just start plugging in big numbers. What's 3 over a million? 3 over a trillion? What's that getting closer and closer to? 0. The dots, the terms are getting closer to 0. Now, do you recall that from our pre-calc class? The highest current at the top. Oh, and I apologize, I wanted to make 3 different examples. Can we put an n squared there? Can we put an n squared there? Just for an example. Do you recall that from our pre-calc class? If you got a rational expression, rational polynomial, and the powers are the same. Do you remember what the Horace was? You got it, Andrew. He says, look at this. I'm going to hide the 1/2 here. Hide that. What's that 3 over 1? Just the value 3. So this thing actually has a horizontal asymptote. This one was at y equal to 0. This one's at y equal to 3 in terms of y's and x's. You know, we call this n and this a sub n. 1, 2, 3. This thing has a horizontal asymptote right at y equal to 3. And that's where it's heading towards. So, and what's the limit as n approaches infinity of this sequence? 3. It's 3. Now, I looked at that graphically because, oh yeah, I remember that in Greek calc class, the rational function. Hey, I'm going to erase this in a second. I'll show you how a textbook would write this. Like how would a solution commander write that out? It's got a lot more writing, where some of you might just go, hey, that's just 3. Because you recognize the what? That the highest power matched the highest power on the bottom is a rational expression. Now in this case, the highest power on the top is a little bit more than this. This doesn't have a Horace. This has a slant asymptote. It has a slant asymptote. Okay. Well, that means that when this thing's either heading towards infinity or negative infinity, you already know the answer? This thing is either heading towards infinity or it's got a slant asymptote. Well, it might slant that way or it might slant that way. You already know the answer? Determine whether the sequence converges or diverges. If it converges, find the limit. Well, this thing has a slant asymptote. What do you mean? It's either going up like that, and then the graph just heads towards it? See, that's what's happening with this. The dots are either coming down here. You can even check this. What's a 1 over 1 there? That'd be 4 over 3. That's like, what, 1 and 1/3? We were here, but these dots would have kept getting closer and closer towards that 3. But in this case, for like the slant's either going this way or that way, it's either heading towards infinity or negative infinity. What are we going to say for this answer? Yeah. This sequence is divergent. Diverges. But, can I talk about it? Can I help you find the slant asymptote? If you do long division, you can find the slant asymptote equation. There's no need for that, though. Please feel free to do that. Do you remember doing long division? Yeah. You can find the equation of the slant asymptote. I say, since we know it's a rational function, would you just reduce that? What's n squared over n?
Just n.
Just n. What's y equal to n or y equal to x look like? Y equal to x looks like what? A line like this, right? So, what's this graph going to do? It's just going to head towards infinity. The dots are going to head towards infinity. The terms are going to head towards positive infinity. So that's why we're saying this sequence diverges. Cool. Hey, great. I wanted to start with this example because you notice they're all very familiar. They're all rational expressions.
Is the rule for the horizontal asymptote 3 divided by 1, or it's just...
Yes, so if this had a 2 here,
Maybe 3 divided by 2.
it would be 3 divided by 2. And that's at the highest power match, the highest power in the bottom.
Okay, thank you.
You're welcome. And when I wanted to start with these examples, because they're very familiar, You could recognize them, but now let's put some ones, I'm gonna pull some from the book, like cosines and what if they have exponentials and all that stuff, right? But these come, we've seen before. Oh, and can I erase this? So this converges to what? 3, you can write it like that. This sequence here converged to 0. Notice I'm saying sequence. So we get the series, it's a different story. And what about this sequence? This sequence diverges. If you wanted to know where's it heading, well, it's going towards positive infinity. Okay? As n approaches it. You can think this. As n approaches infinity, what's a sub n doing? It's going towards what? You follow me? What's going on here? As n approached infinity, what happened to a sub n? It was approaching a what? 3. That's notation you can use. Little arrows. And what happened here? As n approached infinity, what was a sub n doing? It was approaching the 0. Okay, so I'll leave that up here. I wanted to show you, how would a textbook write this? Do you remember in a pre-calc class doing something like this? What's the highest power, n squared? So what I'll do is I'll multiply a 1 to this expression. I'm going to multiply 1 over n squared over 1 over n squared to this entire expression. Okay? What would I get? 3n squared over n squared plus 1 over n squared plus, oh, in the denominator I'd have n squared over n squared plus 2 over what? This is what a textbook would write. And then they would write in all 4 of these places, lim, n approaches infinity. Again here, I think I could squeeze it in. Lim, n approaches infinity. Here, the limit as n approaches infinity. And right here, I can squeeze it in right there, the limit as n approaches infinity. So, what's going on with the limit as n approaches infinity of this? N squareds cancel, what do you get? That's a 3. What's going on with that mathematically?
0.
That's going towards 0. So you're going to 0. You're going to 3. What's this going towards?
1.
You're going towards a 1. What's this approaching?
0.
So look at this fraction. What did you get? 3 plus 0 over 1 plus 0. What's the answer? 3. So you can think like this. That's an algebraic method, an algebraic approach, where I said, oh, I'll multiply a 1 to this expression. And I used 1 over n squared because that was the highest power limit. Right? You could have done that with this problem and that problem as well. Here, just multiply n over n now. Does that make sense? I'll leave that up, because you can always look at that. Paper guy, I know it takes a while to copy all that. That's what you'd see in this actual solution manual for that problem. I mean, can you multiply 1 over n over 1 over n to any of these? Sure. Can you do 1 over n to the 3 halves over 1 over n to the 3 halves? Let me define these limits. Okay. Everyone from 23 to 56. I want to make sure I get a few of these. I'll change them up a bit, okay? But they go quickly. This is like number 23. So like 23. I don't want you going back and saying, gosh, you did all those rational expressions, but I don't know how to do this one. Homework. They go quick though. They go quickly. 3 minus 0.3 to the n. The question, determine whether that sequence converges or diverges. If it converges, find the limit. Don't worry about that 3 right now. Concentrate on that. 0.3 to the n. If you have anything that's lower than a 1 being raised to the n, guess where it's heading?
0.
It's heading towards that right there. It's heading towards a 0. So I'm thinking this is what? What is 0.3? That's 3/10, right? That's like 3 to the nth over 10 to the nth. But if this number right here is less than 1, and it's exponential, you got an exponential less than 1 in terms of that's the base. of the exponential expression. As n goes towards infinity, I'll call it the base. Your base is less than 1. As n approaches infinity, what's going to go on with that little sequence right here? This will head towards what? 0. Do me a favor though, if you're not sure, explore it on a calculator. What's 0.3 raised to, let's do the 1,000th power. What's 0.3 caret 1,000? I want to see what it says.
0.
It just says 0. It's telling you, it's, you know, it's approaching 0, but it's just saying that it's 0. So is this sequence looks like it's convergent. Be careful though. Is it converging to 0, the overall sequence? Good job. Outstanding. Because he says it's convergent to 3. Because it said a 3 in front, right? There's the 3, minus this is approaching a 0. So what's the limit as n approaches infinity of this sequence? 3 minus 0 giving us what? 3. This sequence is convergent. Hey, but in your notes, talk about something like this. Any exponential expression, you know, raised to the nth power, if the base is less than 1, it's always going to approach what? The sequence will always approach 0. Now, what if it was just 1.1? I'll put that over here. What if it was just 1.1? You remember about exponential functions? I'm sorry, guess what's going on with that? As n approaches infinity, you know where this is going? This sequence right here would head towards infinity.
Overflow.
It goes over 1.1. I didn't do 1 though. What would happen with 1 to the nth? That's a trick question. It's a bunch of dots, but what would all the dots be? It's a trick question. All the dots would keep being 1. Oh, they're all, they'd all be 1s. So the limit would be what? Yeah, just a 1. What you're concerned with is that base is less than 1 or higher than 1. Cool. That was awesome.
So if that 0.3 was a 1, would it end up being 2?
You would say that in terms of this problem, yes, if there was 3 minus n, with the 3 included,
Yeah.
Connor's question, he goes, what if you had, they do the trick question at you, right? And they go 3 minus, and they just wrote this 1 to the end. They're like, no matter what, 1 to the millionth, it's still just going to be a 1. 3 minus 1 giving you conversion to 2. And that graph would look like a bunch of dots of 2s. So it helps, I would always think these graphs are dots, and you're trying to see what's going on with those dots as n approaches infinity.
I see there's like a little n on the TI calculator. Is there like a series or sequence model on the calculator?
Sure, I can show you that later. You bet. You bet, especially when we get in a series. You can use the list, you can put them in a list. There's a list button. That's kind of cool. All right, Owen, here's the next one. They go rather quick, so I don't want to rush you. Okay, we already did one like 25, or when that has the rational expression. I'll look at, okay, we got to do one like 27. You haven't seen that yet. I didn't even change anything. That's a good class problem. What's going on with that sequence? Well, let's start with the exponent. See, it wasn't just e to the n. We know that would explode towards infinity, wouldn't it? The base is greater than 1. Can we just concentrate on that?
That goes to 0.
That's going to 0. So does everyone agree? As n approaches infinity, this exponent is heading towards what? 0. So, I got to be careful in my final answer. Is my final answer, it converges to 0. Hold up, what's still sitting there? So what's e to the... He's saying this is heading towards a 0. What's e to the 0 power? 1. So what's the limit? As n approaches infinity of the sequence, it's converging to a what? 1. Because this right here was heading towards 0. Does that make sense? You can even write that if you want to. I'll give time in your notes to go, exactly this right here would head towards 0. And you're thinking like this. E, limit n approaches infinity of 1 over n. E, this is going towards 0. Give me an answer of 1. The sequence will converge to 1. I didn't want to change 27, but I guess I'll change it now. then what's this problem? If I put that on the desk. So, find the limit of this sequence. As n approaches infinity. What would you get?
Yeah, go to 0, anything raised to 0.
2 to the 0 is 1. Very good. That would be a 1. This one came out to a 1. I could play around with this base, make it a 1. 1,000 to the 1 over n. You're still going to get what? 1. I love it. Does everyone agree? That's why I want to change these up. I'll give you sometimes the actual problem. Let's just switch it up a little bit. You're always getting 1 there. Okay. Hey, a few more before we do the next section, which I know you're going to love. We got to get some. I'm looking for. Okay. What if it's got that -1 in the end? I just found one, everyone. I'm going to change it up a tag. -1 in the end over, how about 3 squared of n? I saw the book at 2 squared of n. So this is number 33. They go quick. Just a few more. Do you recognize the top, Katie? What's it doing to the sequence? Oh, this is making it alternate. Plus and minus, plus and minus. And when if you think of the graph, the dots, what will the dots do? They'll keep what? Right? But the question is, are the dots doing this? And never converging it. Or are the dots maybe doing something like this? And it's heading towards like a 0 or something, right? So I didn't want you to think every time you see this, oh, it's divergent. Oh, let's be careful. Just because they're alternating, it might what? Keep alternating, approaching like a value of 0, right? You could see that. That would converge to a 0 in terms of the dots. So this is alternating between a plus and a minus. And here we go again. 1 over 3 squared of n. Where's that heading towards? Yes, the denominator is heading towards infinity. We know what happens to this. This thing is heading towards what? 0. This sequence is converging to 0. And those dots would look like that. Let me draw them again. Like, what's going on? Plug in a 1. You get -1 over 3. -1/3. Okay, that'd be here. You plug in a 2. I get 1 over 3 times the square root of 2. Right? But eventually, what's going to go on with these? It's going to 0, so I'm going to write down the limit as n approaches infinity of a sub n. It converges. It converges to 0. But this was alternating p plus and minus. Great job. Hey, I told you I want to switch it up a little bit. Wouldn't this be the same? Same answer? Where's it converging? As n approaches infinity, where's that going? And q is because there's variables in the denominator, right? Higher power on the bottom, even with a negative and a positive. Hey, let's get some trig functions in here. Let's get some trig in here. Okay, this is like number 35 and 36. Let's get some trig in here. This is like 35. A sub n equals sine of n over 2. Let's think about that sequence. 36 does something like this. These are like these problems. You get 2 totally different answers. By the way, the book, problem in the book has a cosine. And when this goes towards infinity, right? I'll hide this. That expression is heading towards infinity. So now you and I are going to think about the sine graph. What's the sine graph do as it heads towards infinity? I think it's not, it just keeps doing what? It'd be a bunch of dots, but what would these dots do? I'll use my hand. What would these dots do? Just keep going up, wouldn't it? Now it's between a -1 and a 1. So we can't say, oh, it converges to some numbers between -1 and 1. Sorry. In order to converge, it's got to converge to one concrete finite number, so we're going to have to say what? Yeah, well, we'll say divergent. I'm with you. The limit, you could say this, just to add some notes. Okay, I'll do that. Limit as n approaches infinity of this sequence right here does not exist. But that means the sequence is what? Divergent. To be divergent, it means the limit does not exist, or the limit heads towards infinity, or the limit heads towards positive. But according to the directions, Katie, it said determine whether it converges or diverges. We could have just said this sequence is divergent. How about this one though? You are good. So hide this. What's heading towards?
0.
That's heading towards 0 as n approaches infinity. And what's the sign of 0?
0.
So the limit as n approaches infinity of this sequence, I'll put an equal sign to 0. This sequence converges to 0. Hey, I bet you could quickly do a homework problem in your head. The problem in the textbook had a cosine here. That answer is not 0. What would it be?
1.
Because the cosine of 0 is what? 1. Does that make sense? Any other weird ones?
Yeah.
Well, this is the one with the. Oh, I see it. I'll do 31 last. And when I want to do some relationships here, you tell me what's going on with this. What if I stick a polynomial on the top? But I do exponential on the bottom. What's your hunch? You probably know this from Calculus 1, just dealing with limits in your experience. They're both heading towards infinity. But my little trick doesn't work anymore if that's not a rational expression. Which one's heading towards infinity quicker? The exponential expression or the n cubed? The numerator or the denominator? Which one's getting quicker to infinity? If you plug in 1 and you plug in 2, you could just test it. You could just plug in a 4 to both of these. Plug in a 4, and see who's higher. Right? What's 4 cubed? 64. What's 3 to the 4th? 81. Who was higher? Well, that guy was higher. Now, go way higher. Go to like 100th power. You're like 100 cubed versus 3 to the 100. This is going to be way, way bigger than this. So guess what's going on with this sequence? It's heading towards what?
0.
0. And if you're wondering why, it's just because this is much rapidly increasing than this one. Now what if I flip them? What do you think the answer is? What if I got an exponential over monomial? What happens in that race as they're both getting approaching infinity? This is going to explode, yep, and I guess the limit as n approaches infinity of this sequence is infinity, so I can say this would be what?
Divergent.
Divergent. The sequence is divergent. See the difference? Does that always happen with monomials? You bet. I could have done n to the 100th power. Can you believe that? Look. N to the 100th power. Like monomial versus exponential. This is still going to win. You might not see it at the beginning, but you got to get really, really big. Now there's another way we got to do. We just did monomial versus exponential. Who exploded much more rapidly? The exponential, right? As n approached infinity. You agree? What about an exponential? I did 3 to the n. Let's do 2 to the n. They're exponential. They grow exponential, right? Like bacteria. Yeah, but what if they're raised in a factorial? So the first thing is I got to make sure there might be people on the seats right now who don't even know what a factorial is. So can we talk about that? That's called factorial. N factorial. So let's look at some of these. If someone in this class is like, I've never seen that before, it's an explanation point. There's so many dots on the board. I got to make sure I really show this really big. So you get that. An explanation point. Factorial. So what is 3 factorial math? 3 times 2 times 1. What's 2 factorial math? 2 times 1. What's 1 factorial? 1. And if you're curious, someone 0 factorial is actually 1 by definition. We don't have any negative factorials. But these get pretty doggone big. I mean, 5 factorial is already at What's 5 factorial? We can read it. 5 times 4 times 3 times 2 times 1. You're already at 120. 6 factorial, you're already at 720. These get huge really quickly when I'm talking about increasing n. You follow me? So if you're wondering, who's going to increase much more rapidly? Let's explore it. So when you got your calculators, who's bigger? 2 to the 10 or 10 factorial? What's 2 to the 10? I'm just curious. Versus a 10 factorial. Like, who's much bigger? And you can be able to figure out this limit as n approaches infinity. What's 2 to the 10?
1024.
1024. Okay, 1,000, that's kind of big. Yeah, what's 10 factorial?
3,628,000.
3 million? Anyone hear this? Do you see the difference? Who's approaching infinity much more rapidly, much quicker?
Factorial.
This denominator. So where's this heading? The limit as n approaches infinity, a base of n is 0.
I think there is, but I was still thinking.
Hey now, once again, what if I flip-flop these? What do you get a factorial over a exponential? Where's that at?
Oh.
That's divergent, isn't it? What's the limit? As a sub n, as n approaches infinity, this is heading towards what? So I guess exponential was so powerful, it was beating everything until who came along?
Factorial.
Mr. Factorial, right? Now if you're curious, can anything beat a factorial? Actually, something could beat it. How about n to the n? Don't you love math? It's fun. Can you think about n to the n? You want to look at that?
Oh.
Yeah, you go, no exponential. You go, well, hold on. What about n to the n? That's a totally different story, isn't it? Let's just look at, whoops. This stuff's fun. Let's just look at like a 5. Can you check out 5 to the 5th power on your calculator, which versus 5 factorial? Well, 5 to the factorial would be a what? 5 times 4 times 3 times 2 times 1. You know what 5 to the 5th is? 5 times 5 times 5 times 5 times. You see what's happening? Who's going to win that race? And I guess we could go on all day. Who can beat n to the n? How about n to the n to the n? And then that to the n. Do you follow me? This stuff's fun. Hey, great job. We're about to do 11-2, but I thought there's one problem in the notes that might bug you because they got it right. So, this is number 31. Can you help me out with this? They want you to find the limit as n approaches infinity. They want you to determine whether the sequence converges or diverges. I'm sure you can change this up, but I'm going to get you. My hint is, I know it's not a rational expression. When I can do it long way like the book. Remember what the book would do? Yeah, I'll tell you what they look at too.
Separate the fractions.
Sure. But I want to do something. I'm going to hide this. What would that be? Just that part right there. I know it's not a rational expression, but we'll get this answer real quickly if we look at it this way. That's n squared, right? That's n to what? 3/2. So look at what you really have. You got an n squared in the numerator versus a what? Where's the higher power? Where's this heading? This is heading towards infinity. Do you follow me? I mean, you can write out all the notes like I was saying. You know, I was saying to Nicholas, we can do the limit. You know, you divide out like an n cubed here in a radical, an n cubed in a radical, etc. Or n to the 3/2 if you want to do all that. I've seen students spend like 10 minutes doing that. And it looks great. And then they give me the answer. Oh, the answer's a third or something. I'm like, oh. So I really want you to focus, keep it simple, right? It's like, keep it simple. Keep it simple. We're like, can we just look at this and go, all right, this is really what's powerful. We want to look at what's going on with that. And you got an n squared over what? And this is heading towards infinity because that power is higher than that power. So I'm going to write it down here. The limit as n approaches infinity of a sub n, it's divergent. Super job. There weren't any other weird ones, were there? Oh. one more. And we'll have fun with the series. One more, everyone. I know we did factorials, but I didn't do this. Slide number 37. There's a factorial on the top and a factorial on the bottom. This is the sequence. 2n minus 1 factorial over 2n plus 1 factorial. So before we do that problem, let me just look at a simpler example. Before we look at that example, can we look at this? This looks confusing right now. Your goal will be, because there's factorials on the top and the bottom, you're going to want to simplify the expression and get rid of those factorials. We couldn't do that before when there was only a factorial in the denominator with an exponential. We can simplify this. So I'm going to start with this example. How about a very simple example? What's n factorial over n factorial? How does that simplify? Well, that would be n plus 1. What's 1 less than n plus 1? N. What's 1 less than n? N minus 1. I think that's far enough. Dot, dot, dot. It's just going to keep going like that, right? What's this mean mathematically? N. What's 1 less than n? N minus 1. 1 less than that. We get it. Dot, dot, dot. What cancels? Everything cancels out except for the 1. So this is simplified and is equivalent to an n plus 1 with no factorial symbol. Do you follow me? So if that was a sequence, that's heading towards infinity. You follow me? I'll let you copy that, but feel free to think that way. Just keep going and going until they start crossing out. But if you want to see how would the author write this, like in a pre-calc textbook, the author would write this as, I'll wait till you all have a job. I like when you all actually just keep going, oh, it's 1 less than that. It's 1 less than that. It's 1 less than, and then you do it again, you can see everything cancel.
Can you think of it by plugging in a number like
Yes,
2 and like
you sure can. That's a great technique. It's a good problem-solving strategy. You're like, I'm going to plug in a 5. 5 plus 1 factorial over 5 factorial just comes out to being this 5 plus 1. That's a great idea, too. That would work with these, too. If you ever get stumped on them. Hey, the author would write this as this. Simplify. He would say, this is n plus 1 times an n factorial. And what cancels? You know, you wouldn't see what I just wrote in the textbook. So if you like this, think that way, great. If you're like, that confuses me, think the opposite way. Of how you just keep going 1 less than it until you see things cancel. If you got a factorial or a factorial, okay? Just keep writing them out until stuff or cancels out. So let's try this. So I'm going to do it the way I did it the first time. We're trying to get this thing simplified so we can find whether or not it converges or diverges. What's 1 less than 2n minus 1? 2n minus 2, right? Good. What's 1 less than that? 2 minus 3, and we're like, okay, we get it, we get it. We get it. I'll write it again, everyone, just to give it more room. That's 2n minus 1. 1 less than that is 2n minus 2. Dot, 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 forever and ever and ever. Well, what about this guy? Well, I'm going to start him way over here. That's 2n plus 1. What's 1 less than 2n plus 1?
2n.
All I need you to do is subtract the 1.
2n.
2n. What's 1 less than that?
2n minus 1.
And eventually, you're going to see things start to what?
Cancel out.
Cancel. And everything would just cancel, except for what? You're out, the rest of this stuff would be out forever and ever and ever, all these numbers would cancel, this sticks. And what's that in top? That's not a 0. That's a big old 1 right there, one. So this expression is equal to 1 over 2n plus 1 times 2n. My goodness, it's a rational expression. That's a rational expression, that sequence. That's what it is. And the higher power's in the bottom. What's going on with that sequence?
Goes to 0.
Higher power's in the bottom, that limit's heading towards the 0, it's converged. Cool.
for a test, we have to show that work?
No.
Or
No, you wouldn't. I know you're going to be doing much with When it comes to the tests, I love when students abbreviate. You don't have to write out, we're gonna get to that in a second. But we do have to justify when it comes to tests. You say, which test did you use for the series? But with this, you wouldn't.
Okay, thank you.
You wouldn't. Someone might have looked at this graphically, right? Hey, again, how would the author write this? He would say this is equal to what? This is 2n plus 1 times a 2n times a 2n minus 1 factorial, and then he would show what cancels. That this just did what? See? Notice I don't have factorials on it. All right. Hey, in your notes, 11.2. Oh, this is a blast. Series. And today we focus on two types of tests.